This shaft will carry the full force of a waterwheel, tons of torque transferred through wood, every hour of every day. If the grain runs wrong, it will fail within a season. If the diameter is uneven by even a few millimetres, the entire mechanism will vibrate itself apart. Before industrial lathes could produce this component in minutes, it was shaped entirely by hand, by men who had spent decades learning to read wood the way others read maps. In the mill districts of Central Europe, in Bavaria, the Black Forest and the Alpine foothills, watermills remained working structures well into the 20th century. As late as the 1950s, many still operated on components shaped without electrical machinery. The main shaft, the timber axle connecting the waterwheel to the interior gearing, was among the most critical. It had to be straight, it had to be round, and it had to absorb continuous rotational stress without splitting or warping. But how did craftsmen, working only with hand tools, produce a shaft precise enough to drive a mill? The men who built these shafts were not general carpenters. They were millwrights, a distinct trade, still active in rural Germany and Austria through the mid-20th century. A millwright learned by standing beside a senior craftsman for years, watching the angle of the adze, listening to the sound of the plane, learning to judge roundness not with instruments, but with the eye and the flat of the hand.
So, hoch, von dir, hoch, noch von dir, noch was höher, ab. Ernst, jetzt der andere Schnurschlag, 46 Zentimeter. Ernst, der Balge weg.
The knowledge was passed through practice, not textbooks, and when it disappeared, it rarely returned. The process began in the forest, sometimes weeks before any tool touched wood. The preferred timber was oak, specifically slow-grown oak from high-altitude slopes, where cold temperatures compress the annual rings tightly. Dense-grained oak was prized for mill shafts because tight grain resists both compression and torsional stress. The millwright walked the forest looking for a trunk of the right diameter, typically 40 to 60 centimetres at the base, with straight vertical grain and no signs of spiral growth, which would cause twisting under load. Once identified, the tree was felled by hand. Two men with a long cross-cut saw. The trunk was limbed, measured and cut to length. Then came the transport. No trucks, no winches. The log was moved on wooden sledges or dragged by horse down to the mill site. In steep terrain, this could take an entire day for a single blank. At the mill yard, the real work began. The log was squared using a broad axe, transformed from a round trunk into an octagonal prism. The millwright snapped chalk lines along the full length, then worked from one end to the other, striking off the corners with controlled angled blows. This is not rough work. Every strike is a decision. If the axe drifts, the flat is lost. If the flat is lost, the shaft cannot be made round without wasting timber. The 8 faces were then reduced to 16 using hand planes, progressively removing corners until the cross-section approximated a circle. The shaft was checked constantly with wooden calipers, rotating it to find high points, which were planed back by hand. For final truing, the millwright constructed a manually operated turning frame, a horizontal lathe driven not by electricity, but by 2 men working a pole and cord system, alternately pulling a cord wrapped around the shaft. With each pull, the shaft rotated a half turn. With each release, a foot pedal reset the cord. A third man pressed a fixed scraping tool against the surface, removing wood only at the high points, gradually bringing the full length into true cylindrical form. 1 rotation, 1 pass, repeated for hours until the shaft ran clean. This was the moment the raw timber became a precision component. By the 1960s, only a handful of craftsmen in Central Europe could still perform this work without powered machinery. The knowledge had not been formally recorded. It lived in hands and in habit, and once a generation retired without passing it on, it was gone. The difference between a competent millwright and a master was not visible at installation. It became visible after 10 winters. A shaft with uneven grain orientation would develop a gradual bow under continuous load. The mill would begin to vibrate, bearings would wear unevenly, the gearing would lose alignment. A master-built shaft could run for decades without adjustment. The quality of the work was written into the life of the machine. The watermill was not merely a machine. In rural communities across pre-industrial Europe, it was infrastructure, the difference between stored grain and processed flour, between subsistence and surplus. A mill that ran smoothly was a prosperous mill, and a prosperous mill reflected on the craftsman who built it. The shaft was invisible, buried inside the mill housing, but its quality determined everything above it. Long before precision engineering existed as a discipline, before tolerances were measured in microns, durability depended on judgment, on the accumulated knowledge of men who had shaped the same form, in the same material, across entire careers. The wooden shaft of a watermill is not a primitive object. It is evidence of a different kind of precision, one built from experience rather than instrumentation, and one that, in many cases, outlasted the machines that replaced it. These systems shape the world quietly. If you'd like to see more of them preserved, tell us. Which forgotten craft should we document next?